Hey everyone, welcome. Today we're going to get into the incredible story of a material that started out as, well, basically a huge problem, a cloud of factory smoke, and somehow became a key ingredient in some of the most powerful structures on the entire planet. Exactly. So let's just kick things off with a question for you. When you picture a massive skyscraper or a huge bridge stretching across a bay, what do you think is that secret sauce, that one ingredient that gives it all that incredible strength? The answer is almost certainly not what you're thinking. It's this superfine powder that's actually captured from the exhaust of giant industrial furnaces. It literally begins its life as factory smoke. Okay, so to really get how this furnace dust turned into a super material, we first need to zoom way, way in and understand what it is exactly. So the official name is silica fume, or sometimes you'll hear microsilica. At its core, it's an ultra-fine powder of silicon dioxide, which is the same basic stuff as sand. But that word amorphous is super important. It means that unlike sand, where the atoms are in a nice, orderly crystal structure, here they're all jumbled up, kind of like glass. And that messy structure, that's one of the keys to its power.
Okay, Alex, you said ultra-fine, and that's a word that gets thrown around a lot. Can you kind of put into perspective what that really means here?
Oh, for sure. Glad you asked. Just take a look at this chart. A single particle of silica fume is about 100 times smaller than a grain of cement, and it's thousands of times smaller than the width of one of your hairs. We're talking about a scale that is just incredibly, almost ridiculously tiny. Whoa, okay, 15,000 square meters per kilogram. That number, it just sounds impossibly huge for a powder. How does that even work?
It's wild, right? Because the particles are so small, you can fit an unbelievable number of them into just 1 kilogram. So if you could somehow unfold every single one of those microscopic spheres and lay them out flat, their combined surface is just massive. And that is the secret to its reactivity. It creates this huge area for chemical reactions to happen.
And this really sums up what makes it so special. You've got these perfect little spheres of pure, glassy silicon dioxide. But that last point on the slide, that's the real magic. It's highly pozzolanic.
Pozzolanic. Okay, what does that actually mean in terms of what it does?
That's the million-dollar question. So a pozzolanic material doesn't really act like cement on its own, but when you mix it with water and a chemical called calcium hydroxide, which is actually a weak byproduct that forms when cement hardens, it kicks off a secondary reaction. It basically grabs that weak stuff and turns it into more of the strong structural glue that holds concrete together. So where in the world does this stuff come from? Well, its journey from deep inside a furnace to ending up in a filter bag is just as fascinating as what it can do. It all kicks off with this core reaction happening inside a massive electric arc furnace. We're talking 2,000 degrees Celsius. You take quartz, which is SiO2, and you mix it with carbon from things like coal. That insane heat literally rips the oxygen away from the silicon, leaving you with pure liquid silicon metal, which is what they're trying to make, and carbon monoxide gas. Right, and here's the crucial part. Nobody is trying to make silica fume. It's an accident. As you see in step 2, that furnace also makes silicon monoxide gas. This hot gas floats up, hits the cooler air near the top of the furnace, and bam! It instantly reoxidizes back into these microscopic liquid spheres of SiO2. This is the smoke, which then gets collected in these giant filter bags.
And what about that last step, densification? You have it as optional. Why is that?
Well, because when it first comes out of the filters, the powder is unbelievably light and fluffy. It's almost like handling smoke itself. Trying to transport it is a nightmare and makes a huge dusty mess. So densification is a process that basically clumps the tiny particles together. And that one step, densification, makes a world of difference. The densified version is up to 4 times heavier for the same volume, it kicks up way less dust, and it's just so much easier to handle in a typical concrete plant. Honestly, without densification, silica fume probably would have just stayed a weird niche material, instead of being used all over the globe. Which brings us right to its amazing transformation. Because before people figured out what to do with it, this material wasn't just a byproduct, it was a genuine headache. Oh, a huge one. Back before the 1980s, silicone factories had to pay people to truck this stuff away and dump it in landfills. It was just a costly waste product. But then, scientists started really digging into its unique properties. By the 90s, the research was undeniable, and today it's a valuable product that's bought and sold worldwide. It's a textbook example of what we call industrial symbiosis. And you can see that shift right here in this table. It went from being legally classified as solid waste to having its own international standards, like ASTM C1240. How big of a deal were those standards in changing how people saw it?
They were everything, absolutely critical. Having a standard gave engineers and architects the confidence to actually specify it and use it in their designs. It created a universal language for quality and for performance. That's what turned it from a quirky experiment into a reliable mainstream building material. It basically legitimized the whole thing.
And that brings us to right now. Let's take a look at how this thing that used to be waste is being used to build a stronger and much more durable world.
And the scale of it all today is just staggering. Over 1 million tons are produced and used every single year. We've turned a disposal problem for a few factories into a global construction solution used on pretty much every continent. As you can see, its main job by a long shot is in high-performance concrete, because those tiny little particles are so good at packing into the microscopic gaps between cement grains, and because of that pozzolanic reaction we talked about, it makes the concrete incredibly dense, super strong, and really resistant to things like salt and chemical attacks. This is the stuff you use for bridges in harsh ocean environments or for the foundational columns of super tall skyscrapers.
This quote really just wraps it all up perfectly, doesn't it? Converting furnace dust into a high-value building material. It really is the ultimate trash-to-treasure story.
It truly is. And, it leaves us with a really fascinating thought to end on. Silica fume was once just a nuisance, a pollutant you had to capture and bury. Now, it's essential. And it just makes you wonder, what other industrial byproducts, what other materials we think of as waste right now are just sitting there, waiting for the right idea or the right technology to come along and unlock their hidden potential? What other solutions are hiding right there in plain sight?